Question 2. Rhenium has an atomic number of 75. Define the term relative atomic mass. This came up in a previous A-level past paper question. If you go through the playlist, if you watch every single one, you realize that this is a repeated question. Relative atomic mass is the average mass of an atom, average mass of one atom of an element where an atom of carbon 12 is 12. Average mass of one atom of an element, an atom of carbon 12 is 12. That's for 2 marks, just for definition. So yeah, not learning your definitions can be the difference between a grade B and an A, grade A and an A star. Think about 2 marks. I feel like every paper there's like maybe 2 defined questions, maybe 2 over 3 papers. That's 2 times 2, 4, 12 marks. So yeah. 2.2, relative atomic mass of a sample of rhenium is 186.3. 86.3, and that is equal, and then we want to calculate relative atomic mass of this isotope. So that's equal to 185 times by 10 plus, let's let other rhenium isotope equal y. So we get 185 times by 10 plus y plus y times by 17 over 100. Actually, it's not going to be over 100. It's going to be over 27. I think it's not saying percentage. Anyway, yeah, it's going to be 10 plus 17, which is 27. So don't always assume it's 100, like I just did. Now rearrange it so we get 186.3 times by 27. 5030.1 equals 185 times by 10. 1850 plus 17y. 17y is equal to 5030.1 minus 1850. 3180.1. Y is equal to 3180.1 divided by 17. Y is equal to 187.1, but we just say 187. Does that make sense? Yeah, that's really close to 185. So only 2 difference from there. And then you could double check your answer by substituting 187 in, and then hopefully you get 186.3. But I'm pretty confident we got it right. And if you had spare time in exam, that's when you probably did that, not now. And then it says 2.3, state why the isotopes of rhenium have the same chemical properties, same electronic configuration. Same electronic configuration. And then 2.4 and then 2.5. 2.4 is a big one. It's the 5 marker. So it says a 185 Re plus ion with a kinetic energy of that travels through a 1.45 meter flight tube. We know the kinetic energy is given by that. Calculate the time for the ion to reach the detector. Okay, so we've got the length of the test tube, aka the distance. We've got the kinetic energy. Okay, let's remember the equation. Velocity is equal to distance over time. Therefore, time is equal to distance over velocity times by t. Vt is equal to d. T is equal to d over v. So in order to find the time, we need a distance, which we have 1.45 meters flight tube. We also need the velocity, which we don't have. How can we find the velocity? Well, we know that obviously this is going to be the last step, or the second to last step, but it's just useful knowing what we have to find and how we're going to find it now. And this is how we're going to find it. So we know 2ke over m. Actually, we need to find over m equals velocity squared times by 2 divided by m. Okay, well, we need to find the mass, and the thing about this is we can quite easily find the mass of the iron. Mass of 185 Re plus iron, Re plus iron. Well, it's going to be 185, and because the mass we want it in kilograms for time of flight mass spectrometry, it's going to be 185 divided by 1000 divided by L, which is Avogadro's constant. And therefore we get that m is equal to, well, let's do that. So 185 divided by 1000, or times by 10 to the power minus 3, whichever way you prefer, and then divided by 6.022 times by 10 to the power 23, and we get 3.07 times by 10 to the power minus 25. Three significant figures, this bit. And just before I carry on, 9 times out of 10, if they give you the Avogadro's constant, they want you to use it. Now, that doesn't mean if they don't give it you don't have to use it. It's a bit of a tricky thing. But 9 times out of 10, they give you Avogadro's constant, you got to use it. And with 5 markers, 6 markers, you're going to have to use it at some point when they give it you in the question. So now we've got the mass. Now we can quite easily find the velocity. Yeah, we can quite easily find the velocity squared. So velocity squared is equal to 2ke kinetic energy of 1.153 times by 10 to the power minus 13. 1.153 times by 10 to the power minus 13 all over the mass, which is 3.07 times by 10 to the power minus 25, what we just worked out. Velocity, and then I'm just going to put in my calculator. I'm just going to square root the answer in my calculator. 2 times by 1.153 times by 10 to the power minus 13. Just double check that. Kinetic energy, yep. Divided by 3.07 times by 10 to the power minus 25. And then that's velocity squared. We don't want velocity squared, we want velocity. So then square root the answer, and you get velocity is equal to 86683.3708. 86683.3708. And now we can quite easily find the time, because the first thing I did was rearrange it, and I know time is equal to distance over velocity. Time is equal to distance, which is the length of the test tube, 1.450 meters, over velocity 86683.3708, and then I'll just put the value in here now. So 1.450 over answer, and we get 1.67 times by 10 to the power minus 6. Does it say to round in seconds? Yeah. So there we go. I thought it meant to the nearest second, then I was like 1.7. No, then it'd be 2 then. But 1.67 times by 10 to the power minus 6 seconds is your final answer for 5 marks. and we've got 2 minutes left because there's 12 marks in total. 2 minutes left to do this question. 2.5. State how the relative abundance of 185 Re plus is determined in the time of flight mass spectrometer. This question is pretty much AO1. Well, at the detector, the ions gain an electron. However, it probably wants us to apply it to the question, so the Re plus ion gains an electron, and the relative abundance depends on size of current, or you can say relative abundance. I'm pretty sure you can say this as well, is proportional to size of current, but we'll just leave it as that. So at the detector, the Re plus gains an electron, and relative abundance depends on the size of the current. A detector, Re plus gains electron, relative abundance depends on the size of current, and that is the end of question 2.